Today we're going over 2025 AMC 12B question number 25, which is the last question, the hardest question. Three concentric circles have radii 1, 1, and 3. An equilateral triangle of the side length S has one vertex on each circle. We just try to find the square of the side length of the equilateral triangle. A 6, B 25/4, C 13/2, D 27/4, E 7. We have a few concept review. First one, Ptolemy theorem. And quadrilateral ABCD. The ABCD is a cyclic. That means it's inscribed in a circle if and only if AC times BD, product of the diagonal, equal to AB times the opposite side CD plus BC times the opposite side AD. So that means the product of the diagonal equal to the product of the two pair of the sides add together. If and only if means if this equation satisfied, and then ABCD also cyclic. This is the famous Ptolemy's theorem. The second concept review, in a cyclic quadrilateral, that means the quadrilateral ABCD inscribed in a circle. And then we can point out the opposite angle A and C are supplementary. And also B and D supplementary. So the opposite angle are supplementary inside the cyclic quadrilateral. Quadrilateral inscribed in a circle, we have this property. The next concept is law of cosine. In a triangle ABC, given A, B, and also the angle C, we try to find the length of a C. We have this law of cosine. C squared equal to A squared plus B squared minus 2AB times the cosine C. So this is the question again. We have concentric circle, radii 1, 1, 3. The equilateral triangle of the side length of S has the one vertex on each of the circle. We just try to find the square of the side length of the equilateral triangle. So we can sketch this diagram, concentric circle with the center O, radius 1, radius 2, radius 3 for the three circle, and then the three vertices of the equilateral triangle ABC located on each of the circle with the side length S. We label the triangle. You can see OA is 1, OB is 2, OC is 3. So we can prove OACB is a cyclic quadrilateral. That means we can inscribe OACB in a circle using Ptolemy theorem. So by the Ptolemy theorem requirement, we're going to try to find the product of the opposite pairs, AC times OB, BC times OA. So you can see AC is S, OB is 2, and then BC is S, OA is 1. So that means this becomes 2S plus S, the sum equal to 3S. So we also want to find the product of the diagonal OC and AB. AB is one diagonal, OC is the other diagonal. So you can see AB is just the S. OC is the radius of the larger circle 3. So this is exactly also equal to 3S. We get the sum of the product of the opposite sides equal to the product of the diagonal. Using the Ptolemy theorem, we find out OACB is cyclic. Once this is cyclic, we can use the property about the cyclic quadrilateral, simply just using opposite angle as supplementary, because BCA is an equilateral triangle. So that means ACB is 60 degrees. The opposite angle, therefore, AOB is 120 degrees supplementary to this angle. Since OACB is cyclic, based on the previous property we introduced. So we're going to apply the law of cosine on this triangle AOB. We can find out the square of S. Square of S equal to 1 square plus 2 square minus 2 times 1 times 2 cosine 120 degrees. Cosine 120 degrees is negative 1/2. By directly plugging, you get the square of S equal to 7. We find the answer from here.